we will start solving the Einstein equations for the most important case that we will consider in this course, along with some black holes, namely cosmology. The experimental evidence is that the universe is expanding, and that it has been expanding, as has been known since 1929 now. It appears that the universe is spatially essentially isotropic and homogeneous once you average over sufficiently many galaxies. So on scales of 1 billion light years or larger, the universe seems to be essentially isotropic and homogeneous. And the evidence for that is, for example, collected in the Sloan Digital Sky Survey, which also has fantastic imagery. If you go to www.sdss.org, it's amazing what they have. So that motivates us to consider an idealizing model where we assume perfect spatial isotropy and homogeneity. That's the case that was first discussed by Friedman and Lemaitre. I think Lemaitre was actually a monk at the Vatican. And later it was also picked up by Robertson and Walker. So this means that concretely, we assume that we can model space-time to a good approximation as a manifold, as a Riemannian manifold, which is of the form of an interval cross some spatial manifold. And the metric can be written as minus dt squared plus some scale factor times the metric on space. So this is to say that we are here assuming a simple model where space-time consists of a space that might be expanding and contracting. And whether that space is finite or infinite in size, well, we still leave that open. But notice that we're dealing now with two manifolds here. We have a spatial manifold, just for the spatial slices of space-time. And this spatial manifold, just space literally, will be described by a metric g bar. And it's always the same, but it can get scaled in the full space-time. So there are two metrics now. There is the metric for the model space, so to speak, and then there is the metric for space-time, which consists of all of this. And this means that we have an opportunity to apply our methods of differential geometry to two kinds of manifolds, and we will simultaneously apply it to this model space here, this model of a space, sigma, with that metric g bar. But we can also apply our differential geometric methods to the full space-time. And that's a differentiable manifold governed by that metric g. So you can already predict that there's going to be a gamma and a gamma bar. There's going to be a gamma for the entire space-time and a gamma bar just for the spatial part of it. Not even scaled, just the fixed space-time here. For example, we could model space as being some three-dimensional sphere. It's always the same three-dimensional sphere, but it might be expanding. So we then have Christoffel symbols with and without bar. We have connection forms with and without bar. We have curvature with and without bar. Because we can apply our methods to just the spatial part or to the entire thing. A of t is called the scale factor, and t is called the universal time. We will assume here that this space of this model for space alone is fully isotropic and homogeneous. So that means it looks the same in all directions, that's isotropic, and homogeneous means it looks the same everywhere. So this is symmetry under translations, and that is symmetry under rotations. So we assume that this space here is a Riemannian manifold, sigma with metric G bar. And the isotropy and homogeneity assumption is the assumption that the curvature is everywhere the same, in all directions and everywhere. So it's a manifold of constant curvature. They can be clarified. They can be, classified. So what are the possible Riemannian manifolds that space alone can be described by? Riemannian manifolds of constant curvature. There is not just R3. It could be more complicated than that. So let us look at the Riemann tensor of this model for just space. The Riemann tensor has a bar because it's just this spatial part. There's no time dependence in this. Well, it must be expressible in terms of a constant, right? It's supposed to be describing a space of constant curvature. And that constant will fix the strength of the curvature. Now, the Riemann curvature tensor, therefore, will be proportional to some number k, but it also has an index structure. And remember, there has to be, for example, it has to be antisymmetric in k and l. And also, you can swap the kl and the ij, and so on. You know, there are Bianchi identities and so on. It turns out that because of the various symmetries and antisymmetries, in fact, just the two that I just mentioned, namely antisymmetry in kl, antisymmetry in ij, and symmetry in swapping the first two for the last two indices, that requires already that the Riemann curvature tensor has to be some universal constant times this particular combination of the metric. It has to be expressible in terms of the metric, and this is the only combination that has the right antisymmetry and symmetry structure that we know the Riemann curvature tensor has. Now, once we have the Riemann curvature tensor expressed in the metric, we can then calculate what the Ricci tensor is, which is what we obtain when we contract two of its indices. So we obtain that the Ricci tensor is then 2k times the metric, and we obtain that the Ricci scalar is just 6 times that number k. Now we can use a triad. There's the number 3 in there, of an orthonormal frame. We only need 3 basis vectors because space alone is only 3-dimensional. We know the Riemann curvature tensor, so we can write down what the curvature 2 form is. Remember, to that end, we suppress the two last indices because we consider them, because of using the antisymmetry, now as being part of a 2 form. Here's the basis of 2 forms, and we contract the index k and l with those. Now, using the fact that the Riemann curvature tensor is known up to that number k, which determines something about the curvature's overall strength, we have therefore that the curvature 2 form on the spatial slicing is given by that expression. So that's a very simple form of the curvature 2 form. The number k is also called the signature, and it plays a huge role in how that manifold actually looks like. If k is larger than 0, then it turns out that the manifold that we describe in this way is a three-dimensional sphere, and it has a finite volume. And it is not embedded, right? So you don't have to view it as being a sphere in some 4 or 5 or 6 dimensional space. You can always embed it into a higher dimensional space, but you don't have to. That was one of the main achievements of differential geometry, that you can have a curved space without thinking of it as being embedded in a higher dimensional space. There are theorems that show that you can always embed in sufficiently higher dimensional spaces, but that's not needed to define the curved spaces. Okay, so if k is larger than 0, then we are dealing with a universe which is, spatially speaking, a sphere. If you travel always in the same direction, you come back to where you arrive, no matter in which direction you set off. This is a closed universe of finite volume. If k is equal to 0, then there's no curvature, and we're dealing with just R3, which is of course flat, no curvature, and it's a volume of infinite volume. It's a universe of infinite volume. If k is smaller than 0, then we're dealing with a universe that is a three-dimensional pseudosphere. It has constant negative curvature everywhere, which is a bit similar to a saddle point in a two-dimensional saddle surface. Such spaces, such a universe would also possess an infinite volume. Yeah?
At what point do we lose the possibility of a torus?
We are just not considering it. It would be possible, yes. You could have a zero curvature solution that is just a torus. You could. This is admittedly just the cases of simplest topology. Now, the Riemann curvature tensor has units of length, actually 1 over length squared. And therefore, the constant k also has units of length, actually 1 over length squared. And therefore, we can always choose our units in, we can choose meters, kilograms, and seconds, but we can also choose other units. And we can always choose units, especially units of length, such that this value k takes any arbitrary numerical value that you want. Except that you can't change its overall sign, or whether or not it's 0. So you can always choose your units in such a way that k is either +1, -1, or 0. And that's the tradition, that one chooses the length such that this is the case. So this was just the spatial part, spatial universe, a snapshot of it, so to speak. Now let's look at space-time in its entirety. The metric with our ansatz takes this form, minus dt squared plus a scale factor squared times the metric that we just discussed. And it could be positively, negatively, or not curved at all. Now we define a convenient tetrad, which is a set of 4 basis vectors in the tangent space or cotangent space, which is orthonormal. So our strategy is going to be, we want to solve the Einstein equation using the power of the tetrad formalism so that we don't have to work with actual matrices. At the end of the day, we want the matrices, but it's inconvenient to work, for example, with the Riemann curvature tensor, which has 4 times 4 times 4 times 4 matrix elements. It's just a lot to write down. And so Yes, in this highly symmetric case, you don't have to use the formalism, tetrad formalism, but it's a good way to exercise it, and it's simple too. Okay, so we define now a tetrad in space for space-time. We define a basis vector, one basis vector in the cotangent space to be the dt that comes with the coordinate system, and we define the other basis vectors to be a of t theta bar I, where the theta bar I are the tetrad that we choose for just the spatial part. Remember that everything that has a bar on it is just space. The things without a bar are describing space-time. So these are also normalized with respect to the metric G bar. These are also normal for just space alone. They form a triad. These are also normalized with respect to the full space-time metric. Now, what they are exactly, we don't actually need to know or specify at this point. If the curvature of the spatial part was equal to 0, we could choose them, for example, to be just the dx1, dx2, dx3. But if it's a sphere or pseudosphere, then it would be more complicated. But we don't need at this point to specify exactly what they are. We just need to specify that they are a choice of orthonormal bases. So remember, the theta bar are orthonormal with respect to the metric G bar of just the spatial part, and the theta I are orthonormal with respect to the full spacetime metric. And then we have the structure equation. Remember the two structure equations? The first structure equation is the definition of the torsion. And the second structure equation is the definition of the curvature. And then there are two Bianchi identities too. Now we have, because we have two manifolds, we have the manifold sigma of just the spatial part, and we have the full spacetime manifold M. So we have two structure equations. We have a structure equation on sigma and a structure equation on M. Let's call these equations sigma 1 and M1. So here's the first structure equation. It's the definition of the torsion. Of course, there is no torsion. So the equation really reads, the torsion is equal to this, by definition, which is equal to 0 because we're dealing with general relativity. So that's the first structure equation here. And that gives us a relationship between the d theta and the connection 1 forms. And we have also the first structure equation on the spacetime manifold. Same thing except no bars, because these are now space-time quantities. This is the affine connection on just the spatial part. If the spatial part is R3, this is going to be pretty trivial. But it could be a sphere or a pseudosphere. And in the case of space-time, this is always going to be non-trivial because we are allowing our space-time to be expanding. And the expansion of space-time is, mathematically speaking, curvature between space and time. Non-trivial zero I components of the affine connection. Okay, so we want to determine now the foreconnection, the omega mu nu. To this end, we will calculate d theta I in two different ways. Namely, using the spatial equations or using the space-time equations. So d theta I is what? Remember that the theta I is a times theta bar I. That was our choice of frame here. Right? So the tetrad in space-time is given by this basis vector and these basis vectors, where those form a triad just on the spatial part. Okay, so we have here the d theta is the d of this. By the Leibniz rule, we have those two terms. Now let's use the equation 1, equation sigma 1, which was this one. It tells us something about the d theta bar. Namely, we can express the d theta bar in this way. And how does that evaluate? Well, this is the exterior derivative of the scalar function a of t. Exterior derivative of a scalar function, if you remember, is, in principle, we have here dA by dx mu. But it doesn't depend on any x mu except for x0. So it's really just dA by dx0, which is dt, times dt. Veg this. And here this is what we just calculated using the equation sigma 1. Okay, now the dt is our first frame vector, sigma theta 0. That's just a dot. This is carried forward. And the combination of a times theta bar is really just theta. So we have here, this is carried forward. The a goes together with that, becomes the theta. And here we're just carrying that forward. And here we have a theta 0 and a theta bar I. Let's swap the two, pick up a minus sign. And instead of the theta bar I, let's write theta I. That comes at the cost of having to divide by a, because they are related just by the scale factor. Okay, so now we've expressed the d theta I in one way. That's one expression for it. But there's another way to calculate the d theta I using our equation, the first structure equation for the space-time, namely this one. Right? First structure equation for space-time, torsion equals 0 means this. So the d theta mu is this business. Okay, so that's what we have here. It is this. By the first structure equation, it is this. And we can write that sum over all nu as consisting of two terms. Ones where we have just the term 0, 0, where nu is equal to 0. And then we get also those terms where the j is equal to 1, 2, or 3. Now we can compare. We can compare these two terms to those two terms. And from that we can read off that, where is it? Yeah, this term has to match this one. So we can read off that omega I0 has to be this expression, and this here has to be that. Okay, so now we've calculated what the connection 1 form is in terms of the tetrad and in terms of the connection 1 form of the space, just the spatial part, which depends on what we choose for the spatial part, whether it is just flat or a sphere or so on. Now we calculate the curvature 2 form. Let us remember the second structure equations. The second structure equation is the definition of the curvature 2 form. The first structure equation was torsion. Now, second structure equation is the curvature. Here's the curvature 2 form, and on the space-time manifold, that is the second structure equation. Let's call it M2. Remember, if you write it out in the usual fashion with coordinates and the basis that goes along with the coordinates, then you have this expression here. That turns into the expression of the Riemann curvature tensor is given by derivatives of the Christoffels plus quadratic terms in the Christoffels. A structurally very similar equation, or the same equation, holds also for space alone for the barred entities. And therefore the curvature 2 form for just the spatial part can be written using this equation here in this way, where the I and the j are just running from 1 to 3, but we have to sum over all mu's from 0 to 3. Right? It's just a special, this is a special case of that, where we don't allow the mu and the nu to be 0. We want them to be spatial. Well, then we can write this, we can carry that forward in this way, because we know from above that the connection one forms for the spatial parts are the same with and without bar. That is here. With and without bar, same thing. Same thing, with and without bar, except there's a case where the mu is equal to 0. That's an extra term. But the connection one forms for the case of spatial index here and temporal index there, so 0 here and a value between 1 and 3 there. We also worked out, it's this, a dot over a times theta. Okay. So what we obtain is that, where are we? Yeah, here. This combination has now only spatial parts. You see, this I and j and L are running only from 1 to 3. And we've separated out that extra term which also has a 0 in it. This term is by the second structure equation for just the spatial part. It is just the curvature 2 form on space. And then this term is just carried forward. Now, we remember that the curvature 2 form on space for a isotropic homogeneous spacetime is always of this form. So therefore, we can now write down what the curvature 2 form is on space-time. Namely, it is given by this piece plus that piece, where the spatial curvature 2 form is given by that, or this. Carry that forward this way. And that term here with the zeros in it becomes this term here, because remember the omega I0 is this. Omega I0 is this, a dot over a theta I. And that's what we get, a dot over a squared, because we have 2 of them. Okay. So overall, we now have the curvature 2 form expressed in terms of our frame, as it should be. We can put these things together, and we obtain that the curvature 2 form is this prefactor times this basis here. Except I didn't get the index structure quite right. Yeah, I think I have to lift that index up here. All right. Okay. Very similarly, I leave it as an exercise. You can calculate what the 0i components are of the curvature 2 form. So these were the II components. Similar methods, you get the 0i components, and you get that. Okay. So now we can calculate the Einstein tensor. See, that was not too painful to go through these little calculations there. And now we can read off from there what the Einstein tensor is, and the Riemann curvature tensor is. We can put it all into the familiar framework. So we know that the curvature 2 form, which we just calculated, is really just given by the Riemann curvature tensor, 2 indices considered to be part of a 2 form. So we can read off from that information, the 2 equations in the box. We can then read off what the Riemann curvature tensor is, what the Ricci tensor is, and what the curvature scalar is. And let me skip the details of that. It's just writing out a lot of things. But it's basically just harvesting the information that we obtained by calculating the curvature 2 form. And then we can calculate from that, once we have the Riemann curvature tensor and the Ricci tensor and the Ricci scalar, we can calculate what the Einstein tensor is, which was that expression. Remember, the left-hand side of the Einstein equation. And putting it all together, please verify as an exercise, we obtain that the Einstein tensor, the left-hand side of the Einstein equation, takes this form for homogeneous isotropic spacetimes. Namely, and you see, we are not solving any Einstein equation just yet. We are just expressing the Einstein tensor, the left-hand side, therefore, of the Einstein equation, in terms of the parameters that go into our ansatz, which is that there is a scale factor A of t, and that there is a number k, which determines what kind of curvature we have. So we have that the metric, so that we have now that the left-hand side of the Einstein equation, the g mu nu, is diagonal, because we find that there's only a 0,0 component of g, and an II component, but that the off-diagonal elements are all 0. And the 0,0 component takes this form, the II component takes that form. So in principle, we can choose any arbitrary scale factor, A of t now, any arbitrary scale factor function A of t. We can choose any arbitrary k, and bang, we have the Einstein tensor, the left-hand side of the Einstein equations. Now, what about the energy momentum tensor? Well, we know it's got to be diagonal too, because if the energy momentum, if the Einstein tensor comes out diagonal, and this is the Einstein equation, we are assuming it now to hold, then, well, the energy momentum tensor has no chance. It also has to be diagonal in the same basis that the g mu nu is diagonal. Then, by convention, we write the energy momentum tensor as a diagonal matrix with entries that we call rho, an energy density, and p that we will call a pressure. Remember that this is really just terminology, because it might be the case that this energy momentum tensor is arising from a gas, which has an energy density and a pressure. But this energy momentum tensor might as well arise from electromagnetism, from radiation, or it might arise from a Klein-Gordon or Dirac field, in principle. And the whole thing could be highly quantum rather than being some sort of fluid. It could be all just a quantum field. It could even be just the vacuum of a quantum field that produces an energy momentum tensor, in which case we really shouldn't think of this pressure as being literally a pressure as in thermodynamics. So whatever the origin of the contributions to the energy momentum tensor really are, quantum or classical or whatever kind, we always call the 0,0 component an energy density, and the remainder we call pressure. Also notice that I'm now following the convention of moving the cosmological constant onto the right-hand side of the Einstein equations. So far, we had the cosmological constant appearing on the left-hand side along with the curvature, because by Saharov's argument, that's where it arose. But it is usually today thought that we should keep the Einstein tensor on the left-hand side, and on the right-hand side we have everything else. And that means the energy momentum tensor from all sorts of known matter and inferred matter, such as dark matter, and also the cosmological constant. Now, because it had its origin on the left-hand side of the equation, when you move it to the right-hand side of the Einstein equation, it comes with a minus sign here. Okay? But with our signature convention, where the time coordinate has a minus sign, you see this is the metric here. Remember that the cosmological constant arises in the Einstein equation multiplied with a metric. And when you put it on the right-hand side of the Einstein equation, then you have here a negative sign from putting it onto the right-hand side. And you have here the metric, which has a minus sign. Multiplying with this minus sign means that lambda contributes positively to rho. So a positive cosmological constant will contribute positively to the energy density in the energy momentum tensor. And a positive cosmological constant will contribute negatively to the pressure in the energy momentum tensor because there's a minus sign here, but plus signs over there. Okay? So that's important. Cosmological constant provides positive energy density but negative pressure. Again, interpreting the contribution as pressure, just because in fluids that's what it would be. Now we can ask what kind of matter produces a diagonal energy momentum tensor like that. Well, one can prove that for the energy momentum tensor of any Friedmann-Lemaitre spacetime, so spatially isotopic and completely homogeneous, is always of the form of that of a perfect fluid. And that is because, even if it isn't a fluid, it always has the form of a perfect fluid. And that's because of the high symmetry that we assume for space-time here. And the proof is quite simple. When you have a diagonal energy momentum tensor, then in this framework, you can choose to define the following vector u. It's just the basis vector in the tangent space that points in the time direction. Let's call it we called it E0. And then you can easily check by just writing it out what these things are. You see, this is then going to be a vector which in a suitable coordinate system has only entries 1, 0, 0, 0. You can show that the energy momentum tensor that we just wrote down with the rho and the p, that energy momentum tensor can be written in terms of that vector u in this form. But that is the defining form of an energy momentum tensor of a perfect fluid. We said that any energy momentum tensor that has this form of vector, some scalar part in front of it, and then g mu nu, some scalar part in front of it, that kind of energy momentum tensor we said is the energy momentum tensor of something that by definition we call a perfect fluid. But then if the matter is a fluid, what's the vector field u? Well, in practice, for example, in our universe now, as it is now, it's pretty close to being homogeneous and isotropic. So we are basically in that scenario. And then what is that vector field u? What kind of matter is it? Now, if we disregard the fact that the universe is actually accelerating at the moment, which means that it's no longer really dominated by the mass of the galaxies. Our universe is already being dominated by a cosmological constant, which is contributing about as much as the galaxies are, actually more than the galaxies are and the dark matter are. But if you for a moment consider a universe that is dominated by the galaxies in it, then the galaxies would be that fluid. The galaxies would be the particles of that fluid. And the vector u is then the vector of the flow of those galaxies, of that fluid. Because this fluid is in a sense, not flowing at all. It is only co-flowing. It's only co-moving. You see, the galaxies in the universe have very little motion on their own. They are moving apart from each other, but it's just because the fabric of space-time is expanding. And they have very little motion relative to each other. Some galaxies are close enough to each other that they start attracting each other significantly, and then they start accelerating towards each other. Such motion is called peculiar motion, but it's not the dominant motion in the universe. The dominant motion is all galaxies just moving apart from each other. And if you sit in one of those galaxies, as we do in the Milky Way, then we are not moving, so to speak. We are just, sitting there as the universe expands around us. And in other words, we have a velocity vector which has only a zero component, only a time component. We are not moving in space, we are only moving in time. And that's the vector u. Okay, so the Einstein equation then. The Einstein equation consists of two equations. I mean, in principle, this is a 4x4 matrix, and that is a 4x4 matrix, but they are diagonal. And the space components are all the same. So we actually only get two non-trivial equations out of the Einstein equation because of the high symmetry. Namely, the 0,0 component of this equation, if you go back to the equations that we had above, and you just collect the coefficients, you find that the 0,0 component of the Einstein equation is this on the left-hand side, and that expression on the right-hand side. The II component of that equation is this equation. The first one, the 0,0 component equation, is also called the Friedmann equation. Now let's take stock. What do we have here? Lambda is supposed to be a constant, so it doesn't have its own dynamics. Rho, though, the energy density, we expect to be time dependent. Because if the energy density has such and such amount now, well, if the universe expands, we expect the energy density to dilute. Not always the case. If there was only dark energy, if there was only a cosmological constant, then it wouldn't dilute, because the cosmological constant is a constant contribution to the energy momentum tensor. It doesn't dilute. It's a constant times the metric. That's the contribution to the energy momentum tensor, right? You see it here, right? It would not dilute. It contributes as if it was an energy density, but not diluting. Yeah?
So if you go up one slide up, I think you have for momentum energy stress tensor, you have minus gamma bar.
Minus gamma bar? Where do you see that?
In front of the metric.
Where?
Right turn there.
Oh, here. Oh, here. Minus lambda bar, yes.
Yeah, so we have two gamma bars, so like because with the velocity vector, the gamma bar in front of the velocity vector.
Which is you mean lambda bar, right?
Oh yeah, my bad, lambda bar, yeah.
Okay, and lambda bar is the same as lambda up to the factor of 8 pi g, right?
Yeah, but so you get two lambda bar, and I was wondering, shouldn't it be lambda over 16 pi g?
Oh, you mean as a factor of 2?
Yes.
Let me see. Where is it? Yeah, you see, we have here Einstein equation is like this, and the Einstein equation, if you write it with the energy with the cosmological constant, then you have the g mu nu plus lambda times g mu nu. Not lambda half times g mu nu, but lambda times g mu nu. Maybe you're mixing it up with the Einstein tensor itself, which has a factor 1/2 in here, this one. But the cosmological constant adds to it without a factor 1/2.
Can you go down on next slide?
Okay.
The one with the this is lambda over 8 pi g, right?
Yes.
So the T mu nu has rho ppp minus the lambda over 8 pi g. But
G has only time components.
Hmm?
yeah, so it will be
use 1, 0, 0, 0.
Yeah, so the 0, 0, or the 0, 0 component on the next slide would be 4 pi lambda, not 8.
Why?
The lambda over 4 pi t.
Why? But you see, it's component-wise. This component minus lambda over 8 pi g minus 1.
Yeah, so then if you go on the next slide, the 0, 0 component would be, yeah, 0, 0 component would be rho plus.
Oh, I see. So you're saying.
Lambda bar, which is lambda over pi g. So there's two missing.
I have to think about that. Good point. I have to check that. I don't know by heart. I would be surprised though.
It would make sense if there is no lambda bar in front of the velocity vector.
Yes. Well.
Do we need the lambda bar in front of the velocity vector?
No, that's right. Yes. Yes, we don't. You're right. Very good. Very good. That's it. That is right. Okay. Oh. Okay, great. Great that you spotted that. Very good. Okay. Right. But here it's correct. So we have the lambda here contributing to the 0, 0 component positively, just like an energy density. But here it is contributing to the pressure component negatively. Right? We saw that earlier, that has to come out. And the first equation is called the Friedmann equation. The second doesn't have any particular name. Right. Yeah, I want to say that lambda is a constant, k is a constant. What is dynamical is a of t, rho of t, and p of t. So we have only 2 equations for 3 dynamical variables. Seems to be a problem. Okay, so we need an additional equation that relates those 3 variables. Otherwise, we cannot solve it. It's not going to be unique. Now, we'll get to that in a moment. For now, let's make use of the following observation. This term, the k over a squared, is a little bit annoying because it depends on what value k has. And it turns out that it occurs in both equations, right? Here is the k over a squared. Here is the k over a squared. You know, we can eliminate that from those 2 equations. We just take a third of the top equation and add to it the bottom equation. Then we obtain an equation which doesn't have k in it. Okay, so we obtain then this equation here from the Einstein equation, and it involves no longer the k. From that equation, we can already draw some conclusions. Consider the case of where there's no cosmological constant. Then what conclusion can you draw? Any guesses? Is what? It's negative, that's right. if the cosmological constant is vanishing, A double dot is negative, because the energy density is going to be positive, the pressure is going to be positive, at least with regular matter is going to be. And so we expect that a universe that is homogeneous and isotropic and expanding will be decelerating. In any case, even if it is shrinking, we must have that the second derivative of the scale factor is negative. That's not what we see. What we see is that the expansion of the universe is actually accelerating. And it is not known exactly how to accommodate that today. We could say that the cosmological constant is vanishing and then try to argue for some sort of exotic matter that would make this term negative so that overall the acceleration can be positive. But most theoreticians today favor the idea that there is actually a cosmological constant. Also, there is no lack of theories for making that negative. You could have scalar fields with funny potentials, and they might generate a negative contribution here as well. So independently of whether the universe is a closed sphere, three-sphere, or it is hyperbolic, or it is just R3, this is what matters when it comes to the question of expansion, of whether the expansion is accelerating or not, and what might drive the acceleration. At present, the general picture is that the energy density that we see in luminous matter, in stars, and whatever else radiates in the universe accounts just for a few % of of the energy density that's actually there. And then dark matter is perhaps 30%, and the remainder is made up by a cosmological constant. That's currently the best fit to the data. Now, so the experimental evidence, as I said, is that A double dot is larger than 0 now, and has been for a few billion years. You see, initially, the universe must have decelerated, because initially the matter density in the universe, radiation and matter, was so high that it dominated over that small cosmological constant that we now have. And therefore, this term dominated over that term. So overall, we had here a negative sign. But this stuff, whatever it might be, if it is just regular matter or dark matter, is expected to dilute with the expansion, so that becomes smaller and smaller until eventually this term becomes smaller than that term, and then we have that the cosmological constant dominates and we get an acceleration. And of course, that will only hasten the dilution effect in here. And so then it really takes off. And how does it take off then? Once we have domination by the cosmological constant, how does it accelerate? Well, let us consider the Friedmann equation. The Friedmann equation, remember, that was the 0,0 component. Where is it? Here. Let's say that term is negligible. We just have lambda here. Then we can solve the Friedmann equation in dependence on k. Now, if k is equal to 0, you can already tell what's going to happen. If k is equal to 0, this is negligible, then we have that a dot over a squared is equal to lambda. Or in other words, a dot over a is proportional to the square root of lambda. So a dot over a is proportional to a constant. right? So A dot over A is proportional to constant, meaning that A dot is proportional to A, which is to say it's exponential. The scale factor is exponential if k is equal to 0. If k is not equal to 0, we have some slight modification to it, and but you can still solve it. It turns out that then it's not solved by the exponential function, but by the hyperbolic sign and the hyperbolic cosine. So here is the Friedmann equation again, where I've neglected the term that comes from the energy density. So if it's just the cosmological constant that dominates the right-hand side of the Friedmann equation, then that's the differential equation we have to solve. For k equals 0, it's clearly exponential. For k not equal to 0, we have these solutions. So right here, this is k equals 0, as we argued, proportional to the square root of lambda. And the hyperbolic cosine and hyperbolic sine are also ultimately exponential. So either way, the universe takes off. Explosively, in the sense that it's exponentially. In fact, it can. Okay, I'll talk about that later on. Okay, so but what is the general solution strategy when it's not so simple? Now what we just did was very simple. Cosmological constant dominates everything. Forget about energy density and pressure. Simple. In this case, we had only one equation to solve, the Friedmann equation. One equation sufficed, and one unknown, which was a of t. But really, we have a of t as an unknown function, rho of t as an unknown function, and p of t as an unknown function. And we have the two equations of motion of the Einstein equation, the 0,0 component, the II component. We need a third equation. Okay, so we have three unknown functions of time, and so far only two equations. The third equation has to be the equation of state. There's got to be a relationship between the pressure and the energy density of whatever fills the universe. That does not come from general relativity. That comes from the physics of the stuff that fills the universe most. So if, for example, the universe is filled mostly with electromagnetic radiation, well, then you have to go into the Maxwell equations and find out what is its energy momentum tensor. What is its relationship between the pressure and the energy density? And then once you have that, then you have three equations for three unknown functions. You have a relationship between pressure and energy density on one hand, and the two Einstein equations on the other hand. Together there are three equations for those three unknowns. And as part of the project, play around with this. Make an assumption for the relationship between P and rho, and then see how the universe reacts. How does the nonlinear dynamics of the Einstein equation play out, depending on what assumption you make for that relationship between pressure and energy density. Now, if, for example, there are special cases, let's say the case that we just considered, only vacuum energy, the cosmological constant completely dominates, when in that case, the pressure is strictly minus the energy density. Right? Remember that a cosmological constant contributes positively to the energy density, negatively to the pressure, with exactly the same amount. They are just negatives of each other. So in other words, the pressure is negative of the energy density. That is the equation of state relationship for cosmological constant domination. Remember, I should have maybe stressed that more. The relationship between pressure and energy density, that is what is called the equation of state. And in the case of domination of the universe by cosmological constant, we have one equation of state. In the case where the universe is dominated by, I don't know, dust, it is a different equation of state, and for radiation, yet another one. And here are the examples. cosmological constant, that's the relationship, that's the equation of state. For pure radiation, if you go into electromagnetism, and then for the Maxwell equations, calculate the energy momentum tensor, find out what the relationship is between energy density and pressure, you find that's what it is. The pressure is a third of the energy density. And for dust, there is simply no, and for dust, there is simply no pressure. That's the definition of the dust. There is no pressure. So these are three relationships between the pressure and the energy density, and we can check how the universe behaves under these three assumptions respectively. But how do we do that? In principle, we have three equations for three unknown functions. But how do we most cleverly go about it to solve for these three unknown functions? And here's a clever way to do it, and you may want to do that in the project as well. The key observation here is that the Friedmann equation only contains A and rho, only those two unknown functions, but the Friedmann equation doesn't contain the pressure. The 0,0 component of the Einstein equation doesn't contain the pressure. Let me show you again. Where is it? Here we go. Friedmann equation, 0,0 component of the Einstein equation. It contains A, it contains rho, it doesn't contain the pressure. And so the strategy now is that we try to express the energy density as a function of A. If we can do that, if we can express the energy density as a function of A and plug that into the Friedmann equation, then the Friedmann equation no longer depends on rho and A, it depends only on A. So then we have only an ordinary differential equation for A to solve. And once we have A of t, we can calculate everything. Okay, so the key is we need to find out what rho of A is. Then plug it into the Friedmann equation to eliminate rho. Then we have only A. And the Friedmann equation becomes just a differential equation for A. A nonlinear one, it may require numerical evaluation. Or if you choose your equation of state suitably, you may be able to calculate it analytically, as we will do now for some examples. But first, our challenge is to express rho as a function of A. Here's the proposition. The Einstein equations, A and B, so the 0,0 components and the II components, imply that. You may wonder, where is this from, and how is this useful? Well, I will show you in a moment where it's from. Now, why is it useful? Why it's giving us a relationship between rho and A, if we can solve it. If we have a model for, if we have an assumption for the equation of state, the relationship between rho and P, then we should be able, you see, if P is a function of rho, then we obtain here a differential equation for rho as a function of A. Notice that there's no time dependence or anything of that kind in here. Rho can be viewed as a function of A in here. It's a differential equation in A. So if we can solve that after expressing P through rho, then we obtain a rho of A. And that rho of A goes into the Friedmann equation. Friedmann equation becomes a differential equation for A. That's the strategy. Okay. Now, let's postpone for a little moment the origin of that equation. Show you in a little while. If it is true, it will be, then we can use it in the following way. Assume that the equation of state is very simple. It's a linear relationship. Assume that P is W times rho. Remember, we had this equation of state parameter earlier in the course already. P is some W times rho. And for example, when the universe is cosmologically constant dominated, W is -1. If the universe is dominated by an electromagnetic field, then, as we just saw above, this is 1/3. If the universe is dominated by dust, then W is 0, because the pressure is 0, right? So depending on what the universe is dominated by, W takes different values. Let's assume we are in an epoch of the evolution of the universe in which W was a constant. So it was an epoch in which the universe was, let's say, dominated by dust. Might have lasted a few billion years. Or a period in which the universe was dominated by radiation, very early on. In those epochs, we can assume the relationship between P and ρ to be relatively constant. So let's solve then everything with the assumption that W is a constant. For example, dust. Let's say we are considering an epoch of the universe during which the W was equal to 0, because the universe was filled with dust, pressureless gas. In this case, when P is equal to 0, then the right-hand side is vanishing here because the P is 0. And we can calculate from this immediately that we can see immediately that ρ has to be proportional to a to the third power, a to the -3rd power. And that's because the a derivative is 0, so therefore ρ must be 1 over a to the third, so that it's a constant here. Okay, so the density must be like this. That's very plausible. You see, dust is diluting like the scale factor to the power -3. It's diluting inverse power of the volume. That's what we just obtained from this. And in fact, this is basically a continuity equation. Well, I'll show you in a moment. Now, during an epoch when the universe was radiation dominated, we had that the pressure is 1/3 of the energy density. That comes from the Maxwell equations. And here we have that the energy density is again diluting. However, it's diluting faster than matter would. It's diluting faster than dust would. Have any idea why that might be? Why does a photon gas lose energy density faster than a gas of dust would do? Than a fluid of dust would do? You see, it goes like 1 over the volume, all right, but then there's an extra 1 over a factor. The reason for that is that photons are diluting the same way that dust would, with 1 over the volume. But photons also get their wavelength stretched. And that makes their energy go down proportionally to the stretching factor. Whereas if you have dust, well, dust doesn't lose its mc² of energy. But a photon whose wavelength is being stretched loses its h bar omega, because omega decreases as the wavelength increases. Okay, so we have this power here. And then for pure cosmological constant, so if the universe, in an epoch during which the universe was dominated by a cosmological constant, the pressure is minus the energy density. And when the pressure is minus the energy density, then ρ is equal to a constant is the solution. And you can check that in that equation. I'll leave it up to you. Okay, but where does this equation come from? I mean, it's just to say, intuitively, right, it has to be like that, because we said that the cosmological constant has an energy density and a pressure that does not dilute. That's what this says. Rho is a constant, right? Doesn't dilute. Okay. Right, I mean, if rho is a constant and p is a constant, then this equation is obviously true. Right? d by dA of a to the third gives 3a². Right? Okay. So what is the origin of that equation p? What's the intuition behind that? Well, it's sort of a continuity equation, and you can derive it hand-wavingly in the following way. Consider adiabatic expansion, so expansion in such a way that no energy is exchanged with the environment. Then you have that the change in energy is minus the pressure times the change in volume. Usual classical physics, classical thermodynamics. Now, the volume here, we can identify with a to the third power. I mean, we just take a chunk of the universe. Then its volume will scale with a to the third power. The energy in that volume is energy density times that volume. Therefore, the change in the energy, dE, so d of volume times energy density is the energy, right? Is given by minus p dV, minus p d, the volume is a to the third power. So just calculate the d of a to the third power, you get this. So we obtain our equation in the box already. We obtain this equation. It's really a continuity equation. However, that was, of course, not really a clean derivation of the equation in a box, the continuity equation, because it was just classical arguing. You can prove that exactly, but I think we are probably a little exhausted now. I have it all here, the details of the proof for why this continuity equation really holds in general relativity. And it comes out straightforwardly, but you see it's much more complicated than the simple hand-waving argument would suggest. But just the bottom line of it is, consider those equations that we had here, the Friedmann equation and the II component, the 0, 0 and the II component of the Einstein equation, together with the equation of state equation, which is a relationship between the pressure and the energy density, gives us 3 equations for 3 unknowns, A of t, rho of t, P of t. And I showed you a few tricks for solving the 3 equations for the 3 unknowns. And in the essay, in the project, the idea is to get some feel for how the universe reacts, for how the expansion of the universe is affected by an equation of state. And try what happens, especially try, for example, what happens if the W parameter is smaller than -1. Because the evidence is pointing toward it might be smaller than -1. We don't know what kind of matter or field could possibly drive W smaller than -1, make the pressure smaller than minus the energy density. But you get weird behavior of space-time when you assume that. And so what we did here so far was we looked at particular values of this W parameter. Remember, W was the proportionality constant between pressure and energy density. But we assumed W is a constant. Now, try out what happens if W changes, numerically, for example. You see, when W changes, then you could have that because of the derivative of it. That too could affect how the universe is reacting, how the expansion is reacting. It could be that not only the absolute value of W, I mean, I leave it to you as an exercise to find out. Is it only the actual value of W that matters in the evolution, or is it also the derivative or derivatives of W that matter? For example, when a phase transition happens, let's say you have the universe filled with something that has a certain equation of state parameter, and then it coalesces, goes through a phase transition, and you get something, it's filled now with something else, which has a different equation of state parameter, and that could happen very quickly. You have a very quick change of W. Play around with these things. And feel free not only to model the best approximations to the data, but just play around with how assumptions about the relationship between energy density and pressure impact the evolution of the universe. Because the evidence is that the universe underwent a very non-trivial story of acceleration, deceleration, and it's all about the interplay between the equation of state on one hand and the Einstein equations on the other. So just play around with it in reasonable scenarios, but also drive it to the extreme, just to see, make it pop. All right, okay, that's it for today.